Now I'm going to take a look at a situation where I have an in-between case. I'm working with my example, my binomial probability distribution example of the number of girls out of 10 births, assuming that boys and girls are equally likely. So my value for n is 10, the probability of success in a single birth is 0.5, and I want to find the probability of getting between 4 and 6 girls inclusive. So inclusive means I want to include the 4 and include the 6. There's a couple of ways to do this. I could use the probability distribution table where the probabilities represent the case where x takes on a particular value. And if I want to find from 4 to 6 inclusive, this is the probability x is equal to 4 plus the probability x is equal to 5 plus the probability x is equal to 6. Okay, so it would be the sum of these three probabilities. All I would have to do is add these three up. If I wanted to use the cumulative distribution table, I could recognize the fact that this is going to be equal to the probability x is less than or equal to 6 minus the probability x is less than or equal to 3. The reason why that's the case is because this summation of these probabilities from 4 through 6 inclusive is equal to the sum of all of the probabilities up through 6, subtracting out the probabilities we don't want. So that would be the sum from 0 through 3. So we could use the cumulative probability table to answer that. So the probability x is less than or equal to 6 is 0.828125 minus the probability x is less than or equal to 3. So we're subtracting out 0.171875. And doing that quickly, I get, assuming I didn't make a calculator input error, 0.656 rounded to 3 decimal places. So that would be approximately the same answer if you did it this way, adding the individual probabilities up. Using the cumulative probability distribution is just a little bit quicker.